Good morning, everyone. We will start with the first session in the morning today. Welcome everyone to that. There will be two talks of 25 plus 5 minutes, and then the next two talks will be of 12 plus 3 minutes. The first speaker this morning is Professor StatPhys Day from Harvard University, and will be telling us about universal theory of transport and storage. I'll give you an invitation after. Oh, you can see it.
Yeah. Okay. Thank you for the here. Thank you for organizers for my first time here and to enjoying it. Okay, so I think this is a very varied audience. So I'll try to keep it reasonably broad, although towards the end I want to get my latest results, our latest results, and but hopefully we'll see that it's all quite straightforward. Anyway, so my talk is on an old problem, which really goes back to the very early days of high temperature superconductivity in the early 90s. So we have these stainless superconductors like yttrium and copper oxide, which have a superconducting critical temperature, which can be above 100 Kelvin or so. But and one of the big questions, of course, is what is the value of PC and how do you compute it? So naturally, you would like to try to put that in the PCS theory, but the fundamental ingredient of PCS theory is really Fermi liquid theory. The parent state of the PCS superconductor is a Fermi liquid metal. On the other hand, if you take the IPC cuprates and heat them up, you get a very strange, what's called a strange metal, mainly because its properties don't agree with Fermi liquid theory at all. So if you took a conventional superconductor like aluminum or lead, this would be a Fermi liquid. But in essentially all of the new correlated electron superconductors, including the pnictides and now recently the nicolates, all show this kind of strange metal regime. So in particular, here's a famous plot of the resistivity. So what's been plotted here as a function of hole doping and temperature is the resistivity exponent n. So you just take the logarithmic derivative of the resistivity with respect to temperature, and when n is 2 is the Fermi liquid value, which is you see at rather high doping. But when you get to the interesting regimes, where the superconductivity in this case has been suppressed by a magnetic field, you see an exponent closer to 1 over this foot-like shape. So this has been around. This paper is actually 2009, and just understanding this has been, a completely open problem. I'll tell you about our recent ideas on how to understand this. So one common idea is that this strange metal behavior is due to a quantum phase transition. So this has to be a quantum phase transition in a metal, and so I'll just give a simple example of the quantum phase transition in a metal, although I don't think this particular transition has much to do with the physics of the cuprates. If I have time towards the end, I can say a little bit about what the actual underlying physics is for the cuprates. But it turns out, as I hope I'll show you, and that's the reason for the word universal in the title, in the end, the behavior of this one, the transport behavior of this quantum phase transitions under the right conditions doesn't depend really on the details at all. There's kind of a super universality. Many different quantum phase transitions all behave in the same way. Okay, but first let's consider a specific model. So this is sometimes called the Pomerantz instability. If you go back to the original people who talked about it, these days it's called an Ising-nematic instability. And the idea is you have some system with a, say, on a square lattice, And this is a metal, and that's the Fermi surface. So the Fermi surface has the full symmetry of the square lattice. Then you crank up some interaction, which I'm calling J here. And when the interaction is strong, the system likes to break the symmetry and distort into a rectangular shape. So, structurally, this is just the usual tetragonal to orthorhombic phase transition that's seen in numerous crystals. But here, the idea is that it's driven not by the structure, but by the electrons. So that's why, it's although the symmetry-wise it's just just a tetragonal to orthorhombic, but the physics here is the interaction between the electrons that are driving this kind of structural. Okay, so now there are two possibilities of the square lattice of the distortion, and so you would likely think there's an Ising autoparameter, which are called phi, and this Ising autoparameter is 0 over here and non-zero in the distorted orthorhombic. So now the question is, what happens near this more critical point? So it's useful to actually think about it at finite temperature. If you add finite temperature, then there'll be a finite temperature phase transition where this Ising symmetry is broken below this phase transition line and unbroken above. But the focus of this talk will be in this so-called quantum critical region, where you're studying the physics of the zero temperature quantum critical. All right, so what do we know about such phase transitions? So first of all, if you take the finite temperature phase transition, that's just an Ising symmetry of a quantum system, but nevertheless at finite temperature. And what we know is that, in fact, the usual E equals to Ising model, which I think was discussed yesterday too, small by Onsager, the universality class would be exactly the same. Even though this is a much more complicated system, the fact that this Ising criticality doesn't change anything, and it's just a two-dimensional Ising transition. On the other, so if you carry that reasoning along and look at the zero temperature transition, you will say this is Ising in space and time. So maybe it's like the Ising transition in 3 dimensions. Because the quantum time direction is acting like another dimension. So that turns out to be incorrect here. And really understanding that is, of course, the key to the physics of this critical region. So why is that incorrect? So let's try to write down the field theory for this transition. So if you were just doing Ising field theory, you would take some Ising order parameter phi and write down some lambda Ginsburg's potential. And then when S changes sign, you would have the typo field theory, which we know describes the Ising phase transition in 2, 3, and 4 dimensions. However, here the low energy excitation at the critical point where S goes to 0 are not just the Ising order parameter. There's also low energy excitation of the Fermi surface that are present not just at the critical point, but actually everywhere. And so we have to ask what happens to these low energy excitations right at the critical point. So you take the Fermi surface of these fermions, and then there's usually some symmetry around so-called Yukawa coupling, which couples the appropriate symmetry combination of the size. I've left out all form factors and indices, so that I could cite that combination that will couple to phi. So this is the theory you really have to study. And this fact that this Fermi surface is important was pointed out by Hertz, I guess sometime in the 70s, in a famous article on quantum phase. Okay, so this is the theory you have to study. And since the time of Hertz, this theory has been studied a lot, and it's pretty well understood. So what we know now is that this point here is what we call a non-Fermi liquid. It's a state of matter where the Fermi surface is well defined. It's still a very sharp Fermi surface, but the quasi-particles are very short-lived. There are no quasi-particles at all. So this is a strange object which I don't have time to explain because it won't be that crucial for what I have to talk about. Anyway, so this is now fairly well understood that there's a new phase of matter here, which we call a non-Fermi liquid. But what took some more time to understand, and really was only understood well in the last few years, The one hope would be, okay, let's take this non-Fermi liquid and raise the temperature. Do you get a strange metal? Is this a strange metal for this model? And what we've understood only in the last few years, although they were interested all along, we didn't believe it quite a long time ago, but now it's fully well established. The answer is no. It's not. In fact, it's a perfect metal. So we have this strange thing where even though the quasi-particles near the Fermi surface are not well defined. So if you did photo emission, it would not look like a Fermi liquid at all. But if you did transport, like resistance or thermal conductivity, it would look just like a Fermi liquid. And why is this? Well, one way you could kind of understand this goes back to important paper by Walter Cohn, written in 1961, where he showed that if you take an interacting electron gas with Galilean invariance, all the strong interactions make no difference to the form of the conductivity. Conductivity is essentially that of a free Fermi gas. Now, you might think this is very special to Galilean invariance, but what we've understood more clearly in recent years is that since everything depends on near the Fermi surface, then whether you have Galilean invariance or not is really a high energy property. So in fact, even though your system doesn't have high Galilean invariance, near the Fermi surface, it looks like it does. And that's kind of what leads to this problem. Okay, simple to state, but with many wrong papers along the way by famous people, it's something now being understood fairly well. I think everyone seems to agree this is correct. All right, so that doesn't work. So now I can start the real part of my talk. What's going to work? So the hypothesis we took, well, you've got to have impurities. You've got to put in inflation disorder. A few other people have said, well, maybe you have to have Umlauf effects. But those are, very weak at low temperatures and really depend sensitively on the type of crystal. But the strange metal behavior is ubiquitous. It's in every system. And what's in every system, despite the claims of the experimentalists, is a lot of impurities. Okay, so we need a theory with spatial disorder. So I take this theory that I just told you about, the Hertz theory, and let's add in spatial disorder. So there's various terms you can think of. There's the impurity potential. All the terms in blue are associated with some impurity. There's a potential that acts on the fermions. So we just take this to some random potential. And this is the term that's shaping the usual theory of the disorder of Fermi liquids and Anderson localization and all that. So there's a huge theory of the effects of this V of R on a Fermi liquid. So that would be natural to keep, but it turns out that's not the most important thing. If you do kind of a Harris spectrum analysis, you find that the most important thing is this random mass term here, which shifts the local position of critical points. So one side of the sample has a critical point here, and the other has a critical point there. And so there's this random delta S that you can keep. And all of these were looked at before. And it was found either they were not important or they were so important you didn't know what to do with it. But this turns out the key to progress has been realizing that there's a way to just get the right type of disorder where everything works, and that's put the disorder in the Yukawa coupling, which are called G prime R. All right, so this is the problem we want to solve, and it's still not fully solved, but we think through a lot of analytical work and some new Monte Carlo simulations about being reported not by me, but by Avishkar Patel and collaborators, giving us a pretty good picture of what the problems with the theory are. So I'll try to give you a theory of it, and then ultimately the proof of our theory will come from the Monte Carlo results that will hopefully appear. All right, but before we go there, let's try to find a simple model that's solvable. And this model I'm going to talk about is what people are calling the Yukawa SYK model. So I'll just describe its properties. It's an artificial model, but its solution inspired us to do the more realistic things that I've described after that. Okay, so what is the Yukawa SYK model? Here it is. This is the entire model right here. You have fermions that move on n sides. And in fact, they have no dispersion at all. If you put it, it won't change things too much, but there's no dispersion for the fermion. And then you have a bunch of oscillators, all have the same frequency omega naught. Pi and phi are canonically conjugate. So those are just harmonic oscillators. And let's say there's also n of them. So the L is the, and then finally you couple the oscillators to the fermion. As you can see, that's a similarity to the Hertz theory. But if you Yukawa coupling here. But what makes this problem solvable, and also an interesting way, is that you make this Yukawa coupling a completely random number. Independent random numbers is n cubed of order n cubed numbers there, and they're all independent random numbers with zero mean and drawn from any distribution. Okay. Yeah, so this is the Yukawa StatPhys model, and the remarkable thing is that it's solvable in the large limit. So what you can show, and this goes back to a lot of earlier work, that the so-called Migdal elastic equations, which is sigma is g squared. G squared is the root mean square value of the GIDL. I should draw the graphs here. The graphs will appear shortly. Anyway, so there's a fully self-consistent solution. Maybe the next slide. Oh, sorry. Okay, so this is the complete set of equations. You have a Green's function for the fermions. You have a Green's function for the phonons. So these have some self-energies, sigma and pi. And then there's very simple expressions, this polynomial expression in time for fermion self-energy, just a one loop graph of electron-phonon interaction. And this is the polarization of the fermions coming from one loop graph of two fermions. That's it. So these are equations that were written down in the Migdal approximation, where these generally you tend to take these to be the bare fermions, and the Migdal argument is that that's a good approximation. But here we don't do that. We imagine we're arbitrary coupling little g, and we solve these completely self-consistent. Somebody should have thought to do that before, but nobody thought of it because it doesn't seem like a reasonable approximation. But for this model with random couplings, it is in fact the exact solution. So that gives people motivation, in particular these people here, to just go ahead and solve these equations completely. And when you solve these equations self-consistently and completely, you get a very interesting answer that over a wide regime, the ground state is a non-Fermi liquid. So non-Fermi liquid, there's no Fermi surface here since we don't have even a central space, but there are no quasi-particle excitations. Of course, there's a whole long story behind that. That will be a whole different talk that I don't have time to give, but that's the result I need. Yes. Doesn't matter. This is in any, there's no dimensionality. Every site is coupled to every site. It's like a random matrix in Fox space. Any dimension. There's no dimensionality. It's zero dimension is the way to think about it. It's like a quantum dot. The fermions coupled to a whole multiple. But it's solvable only when you make these things random. Yes. Yeah. Not quite, because then the full Fermi coupling will not be just a Gaussian random variable. It's a little different, but it has basically all the same Fermi. In fact, what you get if you did that is this model that was here that has in certain cases a supersymmetry. It's more similar to the supersymmetric network here. Anyway, so you get some strange exponent delta, where this exponent delta is the solution of some equation, and that's the value to an n when the number of bosons and fermions is the same. And here's kind of a phase diagram at finite temperature. This is the non-Fermi liquid region I was talking about. If you look at it more carefully, there's also superconducting instability, which is nice, I guess. And so then you have a nice solvable example of superconductivity emerging out of a non-Fermi liquid, which is, of course, the key problem we want to solve for the Kimbrel. How does superconductivity come out of a strange metal? This is not a strange metal, but it's some type of metal without quasiparticle. All right, so now we want to take this theory, which is really in 0 dimensions, and put it in 2 dimensions in a reasonable way. And that's what was done in our recent paper, work led by Albert Patel, and my former student, Harvey Goebel, of North Cornell, and former postdoc, Ilya Espelis, who's our faculty at Wisconsin. Paper just appeared a few months ago. Okay, so let me describe what's in this paper. So this is the model from which, we were motivated to kind of by the Yukawa exploitation analysis, and this is the actual model we want to study, where the momentum k is in 2 dimensions, and these are local disorders. Delta functions of R is all 2-dimensional delta functions. There was no R in the previous model. So first thing you realize that there's something in this model that wasn't there in the other model, which is this random mass term. So we said, well, we don't like this random mass term because it's causing a lot of trouble. And if you just look at it, it's extremely relevant. And if you do some kind of substance in mean field theory, you get rather strange looking results. So that didn't seem like we did have a lot of Hamilton. But now we realize what we can do with this theory, at least with the terms written, I can just rescale phi. Rescale phi so that this becomes a constant. And then it will introduce disorder in other terms, like this term here, but maybe that's not as important. That's what getting argument will tell you. But what it will do is change the disorder here. So we rescale phi to absorb the random mass, and then this random coupling becomes strong. So we keep, in addition to the random coupling, also the spatially uniform coupling. So basically what we have done is taken the random mass term and put it into this by this rescaling trick into this G prime. So at this point, this is a trick which could be dangerous because there's some other terms we're generating. So we don't know if it's really going to work, but let's assume it works. And if I have 8 minutes, okay, I will tell you about our recent work. We can now actually see when it works, and then it doesn't. All right. So we just take this theory and apply the same tricks that you apply to the Yukawa exploitation model. And now you get, self-energies that depend on frequency and momentum. But the equations for the self-energies are pretty similar. The sigma is d times g, and pi is gg. That was already the same thing. But there's now a few other terms. This comes from the random potential. This is also sigma is g times d, but there's a delta function of r, telling that this is due to local disorder. There's no disorder here at all. So the blue terms they're very much like a Yukawa exploit but there's a very subtle way in which space and frequencies are all mixed up. Anyway, so you have to solve these equations and then compute transport. So that's, we had enough experience with it that it didn't take too long. We solved this. You can also put it on a computer and solve these equations. But I'll skip all of that and just tell you the basic results. The basic results is we get just about, at least qualitatively, just about every property that's observed in the strange matrix. You get a conductivity that falls off as 1 over omega. That's exactly what optical conductivity results show. You get a resistivity that's a linear function of temperature, and you get marginal thermodynamic behavior, the electron Green's function, the specific heat is T log T, and so on. And we are still doing some work on things like magnetotransport, nonlinear response functions, and all that all looks very promising. So we're pretty confident that at least we're on the right track, but we still have to worry about the fact that we did this trick to kind of gauge away this random mass term. Okay, so in 5 minutes, I can tell you about our recent work. So here, this is a preprint, also with Avishkar, who did essentially the main numerical analysis, which would not have been possible without all the special purpose computers at Flatiron, and another postdoc here about this. All right, so here what we're saying, okay, we're going to really focus on the random mass term and see what its physics is. So, and the fermions, didn't weren't that crucial other than giving you Landau damping. So we just go ahead and integrate out the fermion, and then we get this theory. So this top line is exactly the theory you write down for like a random or Ising model. It's just a random mass term, and phi is your Ising monogram. But because you have fermions, there is a small omega term in frequency that's the Landau damping. I should say at this point, it is important that phi be multi-component. Or I misspoke a little bit. This is really the ON model, right? N is the flavor symmetry of phi. The N equals 1 case is a little different. But fortunately for the cuprate, the relevant order parameter is N equals 2, we think. Anyway, so this is the theory we want to solve. You can think of this as a n vector model in a 3-dimensional cubic lattice, where there's a random potential on each side, so that's constant in time. But because of the Landau damping, there's a 1 over tau squared interaction in the time term. So that's the problem. It's the classical ON model on a hypercubic lattice, on a cubic lattice, with random mass term, which is the same independent of time, and a 1 over tau squared interaction in time. So we're going to actually solve this in a very simple approximation. We've also done more extensive numerical work. But this simple approximation has a virtue that it can be done in real time. So you can get even real frequency results. All we do is we take this theory and we normalize, we take this phi-4th term and we do kind of a Hartree factorization. So that will give you a renormalized random mass. So the renormalized random mass depends on the bare random mass plus the expectation of a phi squared in the flow theory. All right, so now it's a numerical matter of just solving these equations, which Avishkar did. So he's doing a whole bunch of tricks, and I'll just show you the results. So for example, you can measure the boson correlation then, and you see this nice crossing point. So that's the quantum critical point. And then what you can do is you can look at the boson propagator and look at its eigenmode. So these are the eigenmodes of the bosonic fluctuations. And then you measure what's the localization then by the appropriate participation ratio of these eigenmodes as a function of energy. Notice this is a log scale. So at reasonable energies here, you get extended boson eigenmodes. This is kind of what it looks like at point Z. But then you see this remarkable minimum. With the localization is small and starts to grow again, logarithmically at very low energy. So first of all, as long as the bosonic eigenmodes are extended, we will take our approximation as fine. So this regime B was what our previous theory was. But our previous theory now breaks down here. Very low temperatures and very low frequencies. The randomness is far more important than we thought. And so now we have to understand what's going on here. So here the states are localized, and then when you get even lower energies, they get kind of extended. There's one region here, one region there. It's all part of the same eigenstate. Okay, so this actually we do understand we claim, and the fact that this kind of eigenstate would appear at very low energies was something that was already talked about in this very nice paper by Homer Chetan Kurtavadi. I think it's somewhere in India today. I'm not sure where, and Thomas Wojcik. So they looked at exactly this theory with randomness and Jij, the couplings in FJ. So they looked at strong disorderment. And what they showed was that they applied so-called Dasgupta RG on this theory. And they showed that the Dasgupta recursion relations were exactly the same as the transfer-spherizing model of randomness in 2 dimensions. So Jij is the constant plus random couplings, and this is the transverse field, which is this random. Again, constant plus random. And the recursion relations for this are the same as a recursion relation for this theory with Landau aspect. 1 minute left. So I can tell you more in the question period as to what is the origin of this connection. It's discussed here. But from that connection, we kind of understand this logarithmic increase of localization. Then it's this random singlet phase type physics where, as you normalize in the Tasgupta-Mon RG, you go to longer and longer length scales and you get lower and lower energy excitations. That's what's happening. Anyway, so from this, you can compute various properties. This is the boson density of states, fermion self-energy, and the main thing you find is that in addition to this quantum critical behavior, there's this foot-like behavior emerging. We have some more data that I don't have. So the resistivity is also linear in T in this new regime. So the basic idea is that here you have the physics of extended bosons, which is the Yukawa-SYK physics, and at very low energies, you have the physics of the random triangle serializing model. And we claim that in this experimental picture, the extended boson physics applies here, and it seems to be, from all the things we talked about in our previous paper. But what we didn't understand in previous paper is this little foot, and that foot we think is the emergence of the transient serializing model. Stop right there. Thank you.
On what level, what goes wrong and this
Well, for example, if the rescale phi is a grand phi squared graph, so that will have renormalized. So if the states are localized, you would think that's really important. The relevant eigenstates are very rapid variation in space. So I think provided it's extended, maybe the denomination of grand phi squared, which is formally irrelevant, is not that important. Once you start getting localized states, you think that the denomination of grand phi squared is really important for that target. I mean, in fact, you can see that's what's happened here also. This theory of Hoyos and all, they have a Jij. They were ignoring the denomination of Jij.
So in the experiment, like at high doping, you see a normal metal, at low doping, you see a straight metal. Right?
Yeah, this is the experimental thing.
Yeah. So in this doping parameter, where does that go into the model?
So in this model, it's just the mean value of lambda. So in this model that we're studying here, it's this lambda here. It's just lambda. So this lambda here gives you this this crossing point. So this is the orbit phase. This is the quantum critical point. This is the Fermi liquid phase here. And so I don't have the data to show you, but we do have data. If you look here, you would get Fermi liquid. What is the gravity?
What is the gravity model of Yukawa-SYK model?
Well, the pure Yukawa-SYK model, this one, is basically the chartered platform, the same as the ordinary Yukawa model. I mean, it only differs from the value of this exponent delta and the value of the actual number for the zero temperature engine. So the microscopic physics is a little different, but the short chain physics and all the boundary graviton, ADS2, all of that applies to this model.
This one is getting it.
Yeah, so JT gravity is this also. Well, so SYK, in addition to having JT gravity, has a whole bunch of other higher dimension operators. There's a whole tower of operators which are not part of JT gravity, and people just ignore, that's much harder to treat. No one's actually embedded all of those operators in some full gravity theory. People just focus on the low energy Schwarzschild mode, which gives you the JT gravity. So here, the higher dimension operators will be different, but the Schwarzschild physics is exactly the same. No, it's just JT gravity. But another question is, what is the gravity rule of this theory? In two-dimensional theory, that's the physics of the Fermi surface is really important. And all those gravity tools don't really know about the actual, they don't know about lambda damping as well. Yeah.
Yeah, so, when you're constructing your bosonic theory,
Yeah.
so where are you getting the, you're integrating all the fermions, right?
Yeah.
Where are you getting gap fermions here?
No, it's not gap. It's mod omega. That means that the gapless.
So you're integrating all gapless fermions.
Yes.
So you should be getting some long range interactions in
That gives you 1 over tau squared interaction. That's the effect of lambda damping. Yeah. So, that's a somewhat dangerous thing. But we've actually, this is results just will be soon. We've not we, Aviskar and Peter have studied this whole theory in Monte Carlo, and they get results completely consistent with what I'm showing you on the simpler model. The advantage of the simpler model is we can do much larger systems, and we can also get analytically continue exactly to real frequency. So that's the results I'm showing you. We get a huge system. Then look at the beta values here. Beta 320, 100, 100. That we can't do with quantum Monte Carlo. But over the overlapping regime, they're very consistent.
That you know, okay, this is stuff. The next one is by Parabita from Ahmedabad, and she will tell us about